You are not getting voice. Please confirm everyone, is my voice is clear? I think, please confirm everyone.
Yes, sir. Clear.
Okay. Thank you. Thank you. Okay. Okay. So what is Biot-Savart law? Biot-Savart law is, these are the two scientists who have discovered that, or who have told us that how to find the magnetic field due to a very small element. So I will give you an glimpse of that. For example, this is a current carrying wire and it has a current I. Then what he says, that if we take a very small element dl of this wire, this dl element is generally known as current element. And at a point, let's suppose this is a point P. The magnetic field at this point will be, let's suppose this angle is theta. Then what he suggested by the experimental way, that magnetic field B should be mu naught over 4 pi. This is a constant. IDL sine theta divided by R square. This is the magnetic field due to this very small element, or you can say this is very small field dB due to this small element. In vector form, we can also write it. What we can write it? dB is equals to, dB is the small field due to this small element, is equals to mu naught over 4 pi. IDL is a vector, cross R is a vector, position vector, divided by R. This is what magnetic field due to a small element. The most important thing in this relation that you should know is that direction of this field, direction of field will be given by, or will be same as, the product IDL cross B. This is again a very important thing, and we will follow this term all the time in this chapter. This is cross product. IDL cross B is what? This is a cross product. Vector product, I think you have studied in class 11, that is dot product and vector product thing. So the direction of A cross B, or you can say the direction of IDL cross B, will be the direction of magnetic field. How this direction is identified, how this direction is found, using right hand thumb rule. Please give me a hint that how many of you know the thumb rule, right hand thumb rule, how many of you know that? Otherwise, I will discuss it in few minutes, or else I will move further. Okay, I think everyone knows, and everyone knows that. So moving further, this is the Biot-Savart law. Direction is same as the IDL cross B. Now there are some applications of Biot-Savart law. You should remember some relations that's on your screen. First is magnetic field due to a circular loop. I'm not going to discuss the derivation part because it's not mandatory. This is a crash course. So what is the relation? Let's suppose this is a circular coil. And this coil is placed, let's suppose this is our x-axis, this is our y-axis, and this is our z-axis. In which plane this coil is placed? Can you identify? According to this coordinate system, in which plane this coil is, this loop is? In which plane this loop is? Let's suppose it has a current I, radius R. Then at the center of the loop, the magnetic field will be mu naught I over 2R. Mu naught I over 2R. Try to remember this relation. Nobody has replied. In which plane the loop is situated? It will not take a lot of time. Comment. Be quick. Otherwise, I will take few names. Rahul, Ristia, Sushant, Vijay, Sanjina, Mohina, Kasa, Divya, Deepak, Ayushi, Angelina, Devyani. Okay. Please comment, everyone. Now, what if I say that a coil has some turns? Coil has some n turns, or this loop has n turns. How does it look like? It will look like something like that. This is a loop and it has many turns like this way. So this is a coil. It is called as coil. It has n turns. Then what will change in this situation? The situation that will change is you have to multiply the number of turns in calculation of magnetic field. You have to calculate the number of turns like this. Now, the another most important thing in these two situations or all the circular loop situation, what will be the direction? Now listen to me. Because I think that whatever I do, you will see a inverted image of me, I think. If I am raising my right hand, I think you would see its left hand. Is it clear? So there might be a difference. So you have to do it with me. Just what you do, raise your right hand, place it up. I am calculating the direction of magnetic field for this coil. Place your right hand at the loop and curl your fingers in the direction of current. Curl your fingers in the direction of current. Like suppose current is going in the anti-clockwise direction. So you have to curl your fingers in the anti-clockwise direction. By this way, the thumb will indicate the direction of magnetic field. If you do so, then your thumb will indicate the direction of magnetic field. So what I can see here that if I curl my right hand in the direction of current, then my thumb comes outward. So I will represent outward is what? K cap. Outward is what? K cap. K cap is Z axis. Or you can say outward. Or you can say, you can represent it with a circle and a dot. This represents outward. This represents outward. Just give me a hint. Are you able to find the direction? If I ask you another question, then can you answer? What will be the direction? Let's suppose this is a loop and current is going in this way. Find the direction at the center. What will be the direction? Inward. Very good. Sushant, very good. Inward, inward, very good. Inward can also be written as minus k cap. Is it clear? Now give me one more direction and then I will be sure that you know the directions. Give me one more. Let's say this is a loop. Okay, so no one has answered the uh, plane of the loop. This is XY plane. This is XY plane. How many planes can be there? XY, YZ, and ZX. Three planes could be there. So there is another loop that I am presenting here. Let's suppose this is a loop. This is in the YZ plane. In which plane? Y and Z plane. One more thing, it has a current I in this direction. Okay. Another thing, the dotted portion of the loop is inside your screen. Is inside your screen, and the solid portion of the loop is outside your screen. So now you need to identify the direction of magnetic field at the center. What will be the direction of magnetic field? Just give me an answer. Anyone? Sushant, Divya. Okay, nobody else is responding. One new message. Sushant is saying inward. Okay. Anyone else from YouTube who can answer? because these are the basic things. And if you make mistakes in them, then there is no matter. Repeat the question. Okay, I will repeat the question. What is this? There is a loop. Okay, I will redraw it so that you can understand better. There is a loop. This is a loop. This loop is placed in the YZ plane. Clear? YZ plane means the dotted portion of the loop is inside your screen like this. Can you see that? This is the YZ plane. This is your XY plane. Flat surface, this is XY plane, this is YZ plane. So the loop is placed this way. Okay. Now what I'm saying, current is moving in this direction, I. Clear? Now what will be the direction of magnetic field at the center? What will be the direction of magnetic field? One thing to keep in mind, you should curl your fingers like this way in the direction of current, the direction in which current is moving. So you can see here, just look at my hand. I think it is going to be very difficult for you. I just try to reduce the blur. Okay, now you will be able to see. Just focus on my hand. Current is moving this way. I don't know whether it's clear to you or not. Current is moving in this way. This is from outside to inside like this. So what you need to do, you need to curl your fingers like that. And if I curl my fingers in the direction of current, then thumb is going in the left side. According to me, it might change due to the mirror image. So magnetic field will be in the direction of thumb, that is left side. So B is in the left direction, or left direction can also be written as minus I cap. Minus I cap. Is it clear now? So this is the way how you calculate the direction of magnet. This is the most important thing. Otherwise, if you know all the formulas, there is no effect, no value of those formulas until you know the direction of magnetic field, how to find the direction. Deepak, is it clear? Okay, moving further, because I can't take a lot of time. There is another question, another thing that is, okay, yes, sir, very good, Deepak. So now the thing is, the magnetic field at the axis of the circular loop. Till now, we have studied magnetic field at the center. So at the axis of the circular loop, what will be the magnetic field? The relation is on your screen, mu naught over 4 pi 2m r square plus x square raised to power 3 by 2. This is very difficult to remember, I think, but this is a common term. In case of ring, you have seen this term. In lot of things, you can see this term. In case of dipole, electric dipole, you can see this term. So this is very easy to remember. Now, if the loop is very small, what is r here? R is the radius. If the loop is very small, that means radius is very small as compared to x. If radius is very small, then you can ignore r. Okay, very good. Mu naught over 4 pi, very good. Then you can ignore r. If you ignore r, then what will be mu naught over 4 pi 2m over x cube? Now, nobody has asked me what is m, sir. What is m? Can you answer what is capital M here? What is capital M? Can anyone answer? Anyone know? YouTube. YouTube family is very quiet today. Magnetic moment. Very good. Very good. Bhagyashri. So this is magnetic moment. What is its formula? Its formula is N, number of turns. I is the current. A is the area. Very good. Magnetic moment. Very good, Deepak. M is NIA. N is the number of turns. I is the current. Let's suppose this is the current I. A is the area of the loop. A is the area of the loop. It is again a vector quantity. Again a vector quantity. Vector quantity, if it is a vector quantity, then it must have a direction. And the direction of this is calculated by right hand rule. right hand thumb rule. The same rule that we have used previously. This is the same rule that we have used previously for the calculation of magnetic field. Now, is it clear to you? Okay. Try to remember this relation. One more thing that you can see here. If you identify for the electric dipole, we have studied electric dipole. And for electric dipole, field at the axial point, electric field at the axial point was 1 by 4 pi epsilon naught 2p over x cube or r cube, whatever you may write. Whatever you may write, it is x cube or r cube. Let's suppose r cube. So if we compare these two situations, these two relations, one is electric field, one is magnetic field, then the relation is quite similar. This is a constant, this is a constant. 2 is there, 2 is here. This is magnetic moment, this is dipole moment. This is again axial distance, axial distance. So what we can conclude here, that this is a punchline. Listen to me. This is a punchline that a current carrying loop behaves as a dipole. What is the punchline? Current carrying loop behaves as a dipole. It behaves as a dipole. And this is going to be very important thing in your further part of the chapter. So try to mention this punchline. This will be the base of why a current carrying solenoid behaves as a bar magnet. What is the meaning of dipole here? Dipole is nothing but the bar magnet. What is the magnetic moment? This is the same difference. What is magnetic dipole is the combination of two opposite magnetic charges, similar to the electric dipole. And dipole moment is a quantity which has a unit. Dipole is something, a name of something. And dipole moment is the quantity, is a physical quantity. So that's a simple, the difference between electric dipole and electric dipole moment is the same as the magnetic dipole and magnetic dipole moment. This is the same thing. I am not saying that dipole and dipole moment are same thing. Dipole is a name of something. Dipole moment is a physical quantity. Okay. Direction of field will be same or will be calculated in the same way as we have calculated at the center. So there is no issue with that. Moving further. Now this is the most important thing. Field due to a circular arc. Okay. Let's suppose this is a circular arc which has a current I. This is. And the arc makes an angle theta at the center. This is the center O. It makes an angle theta at the center. Then what will be the magnitude of magnetic field? Mu naught I over 2R multiplied by theta by 360. Now you should remember this relation. I can't do much with that. Theta by 360. Now I can give you an example for that. For example, if I say, let's suppose this is a semicircle. This is a semicircle. This is the center. Can you calculate the field? Let's suppose it has a current I and radius R. Can you calculate the magnetic field at the center? You should say B is equals to mu naught I over 2R. This will remain same. R is what? Radius. So radius is R here. Into theta by 360. What will be the value of theta? Can anyone answer? What will be the value of these? Are the end points. Semicircle, you know that makes an angle 180 degree at the center. That is 180. Very good, 180 divided by 360. So can you see that it will be mu naught I over 4R? Clear? This is the way This angle could be anything, 30, 60, 45, whatever it is, but you can calculate this. Clear? Now I am moving. Very good, Veena. Veena, you are very late. I think you have joined late because you have responded very late. Okay. So now, field at the center of the loop. Now there is a question. This is a standard question that you should remember because most of the times it can be asked. So I am going to present a very standard question to you. Let's suppose this is a circular loop. Clear? It has a center, this one, and radius something r. Now, what we have done, we have connected a battery. We have connected a battery across any 2 points. Listen to my words, across any 2 points of the loop. Let's suppose I have taken these 2 points and I am connecting a battery across these 2 points. Mind my words, any 2 points. Let's suppose this is A, this is B. And what I am asking that find the value, find field at the center of the loop. Find field at the center of the loop. So what will happen in this case? Let's suppose as you connect the battery, a current I will start. Clear? After reaching A, there are two paths for the current. In the previous class, we have discussed. One part of the current will go here, other part will go here. Let's suppose I1 is here, I2 is here. Now, you can see that direction of current in the upper part and lower part are opposite to each other. So here comes the standard. What is the standard? This is a standard result that magnetic field at the center will be zero in this situation. So what you should remember, whenever a battery is connected across a loop at any 2 points, the magnetic field will be zero. Try to remember this thing. Try to remember this thing because we can prove it as well, but there is no need to prove. It can be remembered easily and the student remembers it in their mind. This is a very frequently asked question. What you will remember, if you connect a battery across any 2 points of the loop, then magnetic field at the center will be zero. Moving further. So there is a concept test. These are the previous year questions. Have a look at that. The question says, a long wire carrying a steady current is bent into a circular loop. Okay, so there is a circular loop of 1 turn. Okay, no problem with that. We have a circular loop which has 1 turn. The magnetic field at the center of the loop is B. So they are not interested in giving the current and radius. But what we know that for calculation of current, we need some radius and current. So let's assume that current in the loop is I and radius of the loop is R. We have assumed that we will eliminate those things later. Now, according to the question, the field at the center is B is equal to, and what we know that field at the center is mu naught I over 2R. Formula should be remembered. Formula should be remembered. B is equals to mu naught I over 2R. One thing is clear. Option B. Someone is saying option B. Deepak Mane. I think you are correct. B is equals to mu naught I over 2R. After that, what we did, the magnetic field, it is then bent into a circular coil of n turns. Now, if we have increased the number of turns, then radius will decrease. Then the radius will decrease and it will look like that. And it has some n turns. Clear? So now its radius will decrease definitely, and if I say that radius is R, can you see that the length of the material will remain same? So for that situation, you can write length in this case is what? 2 pi r. Length of wire is what? 2 pi r. In this situation, length of the wire is what? 2 pi r is the circumference, and how many turns are there? N turns. 2 pi will cancel. So the new radius will be r by n. This is the new radius. Now, if you write new field B dash is equals to mu naught. This is a circular coil. You should multiply Ni divided by 2, and radius is what? R by n. What it will become? B dash is equals to mu naught n square I by 2r. This n will go upward. Mu naught I by 2r is what? B. So what it will be? B dash is equals to n square B. So which option is correct? Option B is correct. Very good, Deepak. I think Deepak has answered the question correctly. Very good, Deepak. Now, so there is one more question for you. Okay, this is the question. Okay, so this is important question. Deepak, try it out. This is also a previous year question. I think it was asked in 2016 or 17 something. Try it out. Now you can see that the plane thing, XY plane, XZ plane. So that's why I was interested in telling you how to identify the planes, XY plane, YZ plane, ZX plane. You need to identify. Okay. Are you trying, anyone? Veena, Deepak? Okay, listen to me. First thing is you need to uh, understand the question. A current loop consists of two identical semicircular parts, each of radius r. Okay, so stop here. There are two identical semicircular parts. It is clear. Okay, someone has answered A. Very good, Deepak. Very good. One lying in the XY plane and other in the XZ plane. Ayushi, very good. Okay, you are very good. Both the students are good. So first of all, I will identify that this is our X, this is our Y, and this is our Z axis. So let's suppose semicircular loop. One semicircular loop is this. This is in the XY plane. And another semicircular loop is like that, which is in the XZ plane. This is X, this is Y. Can you see that? Can you imagine, can you understand the situation? One is in the upward direction like this in your plane, and one is coming out of the screen. This blue one is coming out of the screen. This is in the XZ plane, and this is in the XY plane. Clear? These are the two semicircles, and both are identical. Let's suppose both have radius r. It's given radius r. Okay. We need to calculate the field at the common center, and current is I. So current is I. Let's suppose this is the current I. This is the current I. So let's suppose this is loop 1, this is loop 2. So what we will do, we will calculate the field due to both the parts and then add them according to the vector rules, because field is a vector quantity. So V1 is equals to, this is a semicircle. Huh? Semicircle we have calculated V is equals to mu naught I over 4R. This is what we have calculated. V2 is equals to mu naught I over 4R. Both are semicircles. Now, if we talk about directions, For the first part, direction is along the K cap. Direction is along the K cap. How you can find that? Curl your fingers according to that. Again, for the second part, B2, this is in the XZ plane. So if you curl the right hand, then direction of current will be in the upward direction. That is J cap. Now, net field is equals to vector sum of both the fields. If you add them vectorally, one vector is along y-axis, one is along z-axis, the angle between them will be 90 degree. I hope it is clear. When both are, one is in the y, one is in the z, then the angle between them will be 90 degree. Can you see that both the vectors are identical? Both the vectors are okay. That's very good. So have you done it, or you remember the answer, Deepak? Have you attempted it in the examination, or you have learned it after the examination? Okay. So what I'm saying, that both the vectors are identical, then net magnetic field will be mu naught I over 4R into root 2. Okay. No issue, Deepak. Now listen to me. This is a standard punchline that I have used here. When two identical vectors are perpendicular to each other, listen to me. When two identical vectors are perpendicular to each other, like this, if I am saying that two vectors, this is vector B, this is vector B, both are identical and are perpendicular, then the resultant will be B root 2. Multiply any of the vector with the root 2. This is your answer. Are you getting my point? So if you cancel root 2 with 4, it will be mu naught I over 2 root 2 R. And this is option number 8. Clear? Okay. I think everything is sorted now. We can move further. You can ask me anything you want in this question. Okay, let me just give you a hint actually. Listen to me. This is again an important thing. It will help you a lot. In the questions where direction is not required, only magnitude is required. And in NEET level or at NEET level, there are a lot of questions in which direction is not involved in the final result. Like this, here direction is not involved in any of the question, any of the options. So try to listen to me. The direction of magnetic field for a loop. The direction of magnetic field for a loop is always perpendicular to the loop. Is always perpendicular to the loop. For example, if a loop is in the XY plane, loop is in the XY plane. This is the loop. Then direction of field will be in the Z direction. Clear? This is clear thing. In which Z direction? It will be in positive Z or it will be in minus Z. That's another thing. That you for that you should use the curl right hand rule. But you have an idea that if loop is in the XY plane, then direction will be in the Z plane, in the Z direction. Now, if loop is in the YZ plane, then direction of the field will be, answer quickly. Loop is in the YZ plane, then direction of field will be perpendicular to this. Very good. X. Very good. Similarly, if loop is in the XZ plane, then direction of field will be in the Y. I think it's very clear now. You don't need to remember this. What you need to remember, the direction of field is perpendicular to the plane. Perpendicular to the plane. Clear? So here you can also use this rule actually. First loop is in the XY plane. So direction will be in Z. This loop is in the XZ plane. So direction will be in Y. Y and Z have an angle 90 degree. Clear? Okay, moving further. I think everything is clear now. Okay. Electric, it's a magnetic field due to a straight wire. This is again an important thing. Magnetic field due to a straight wire. What I'm telling you, let's suppose this is a straight wire AB. It has some current I, and you want to calculate the magnetic field at this point P, which is at a distance A from the wire. Now, try to remember one thing. This A is the perpendicular distance from the wire. This is the perpendicular distance from the wire. And the end points of the wire, like this is end A, this is end B. These end points are making an angle phi 1 and phi 2. Are making an angle phi 1 and phi 2. Then what will be the magnitude of magnetic field? Written on your screen, mu naught upon 4 pi I by A. I is the current, A is the perpendicular distance. Sine phi 1 plus sine phi 2. Where phi 1 and phi 2 are in opposite sense. Don't worry about that. You just remember phi 1 and phi 2. Phi 1 and phi 2 are the angles made by extreme end lines with this perpendicular. With this perpendicular. Mu naught by 4 pi I by A sine phi 1 plus sine phi 2. I think the formula is remembered, or write it down in your notebook, because on the next slide, we will require that formula. Okay. Very good, Tina. You have answered correctly in the explain. Moving further. Okay, so now there are special cases. This is standard formula. Now there are special cases. These special cases are always important for any topic. What is it? Let's suppose first cases. For long wire. Long wire means the wire which has enormous length. Or you can say, let's suppose this is a wire of infinite length. That means its length is like this. Okay, so don't worry. Actually, in finite length, it's not like that it will go from up to infinity. This is not the concept. I will explain it, that what is the meaning of infinite wire. Let's suppose you are calculating field at a distance A at point P. Now, what I have told you, that phi 1 plus phi 2, sine phi 1 plus sine phi 2, you have to use. Now, B is equals to, standard form is mu naught over 4 pi I by A sine phi 1 plus sine phi 2. This is what the standard relation. Now, you can see phi 1 is the angle from this line. So, in this situation, or phi 2, both the angles will be 90. Both the angles will be 90, because wire is of infinite length. If you go up to infinite distance, then this angle will become 90. This is an approximate value, or you can say this is the exact result, that what we will get. Then phi 1 is 90, phi 2 is 90, sine 90 is 1, sine 90 is 1. Can you see that it will become mu naught over 4 pi 2I by A. This is again a first very special result. For a long wire, magnetic field is mu naught upon 4 pi 2I by A, or you can cancel 4 with the 2, or you can write another result, but it's good enough. This is the long wire, case of long wire. Now there is another case that is again very important. I think so. Not only me, everyone thinks so. For collinear points. For collinear points. Now listen to me. What is the meaning of this line? Let's suppose This is a wire. This is a straight wire. Whatever may be the length of this wire, whether it is infinite, small, very small, whatever it may be. But if you, for the straight wire, I am talking about only. What if a point is situated in the line of the wire at any distance, but the point is situated in the line of the wire, either in this direction or in this direction. These points are known as collinear points. This is our wire AB, and these are the 2 points P and Q. You can see both these points are collinear with the wire. This is the meaning of collinear points. Then for such collinear points, B is 0. This is very important relation. For collinear points, magnetic field is always 0. Clear now? Third important relation that you can also form here. This is special case 2. Now I am going to discuss special case 3. For semi-infinite wire. What is it? How it will look like? Let's suppose this is a semi-infinite wire like this. From one end, it is going to infinity, and here it is ended. Now you want to calculate the magnetic field at this point. This is point P at a distance A. Now you can clearly see that the infinite wire, the end which has gone to the infinity, will make an angle 90. So phi 1 is going to be 90. But this end will make an angle phi 2 equals to 0. So if you put these things in this equation, you will get mu naught over 4 pi I by A. Mu naught over 4 pi I by A for semi-infinite wire. Out of these two relations, which two are most important according to me? The first relation and the second relation. These two relations are the most important relation. Okay. I will give you a question on that. Try to solve it out. Okay. So we are not studying Ampere's law at that time. We will discuss a question. After that, we will study Ampere's law. Okay. Okay. I have to delete that question after the completion of the question. So make sure that you are writing it. Let's suppose this is a circular part of a loop. And this is a long wire. Can you identify the situation? Can you identify the design? What is it? This is a infinite wire starting from infinity. It is bent into a shape of circular part and then again straight up to infinity. This is the center O, and this angle is 60 degree. This angle is 60 degree. Find field at O, and it has a current I, and radius is R. Find field at O. Please try, everyone. Again, important. This is kind of previous year question. No, I don't remember the date, but this is a previous year question only. So what you can see here, if I say, whenever you see a question like that, this is the standard procedure that I am telling you. Whenever you see a question which can be broken in different parts, let's suppose you can see that there is a straight wire, there is a circular loop, and there is again a straight wire. then you can break these parts in different numbers. Like this is part one straight wire, this straight wire is part two, and this circular part is part three. So we have broken the design in three parts. Now you can see we have to calculate the field at O. How many of you can see that point O is collinear with the part one? Point O is collinear with the part one. You can see now. So B1 will be 0 because for collinear points field is 0. Similarly, you can see that for part 2, point O is again collinear. So B2 is also 0. Clear? Now for part 3, can you see that it is a circular arc thing? It is a circular arc thing. So do you remember the formula for circular arc? What I have told you? For circular arc, you can see that. This is the relation for circular arc that I have told you. Is it clear? So for calculation of third field, B3 is equal to mu naught I over 2R theta by 360. Now tell me the value of theta. Tell me the value of theta. Tell me anyone who can tell me the value of theta. Someone has told 180, 300. Okay. There is a question mark after 300. So you are not sure. The angle theta is what? This is going to be angle theta. Someone has answered Mohina 300. Very good. This is going to be 300. This angle is 60. Total is 360. So this will be 300. So 300 by 360. You can divide it. And I think that is mu naught I by 2R into 5 by 6. So net field will be similar because B1 and B2 are 0. So net field will be equals to mu naught, or you can say 5 mu naught I by 12R. This is the net field. What will be the direction? Answer quickly. It will be in the Z minus Z X, whatever. What will be the direction of field? Answer quick. I am going to write the direction here. Be quick. Very good. Only Veena is responding from the YouTube. Direction. Direction. Nobody is answering. What you first thing, the loop is in the XY plane. Then one thing is for sure, the direction is in the Z direction. Now, for the exact direction, what you should do, curl your right hand fingers in the direction of current. If I curl my right hand fingers, the current is in the clockwise direction. I am curling my fingers in the clockwise direction. The thumb is in the inward direction. And inward direction is minus K cap. One thing, or you can write it circle, cross inside the circle. You can use both of them. Okay. So I need to delete this question from the screen because I need to discuss Ampere's law on this screen. So I'm clearing it. Will it be okay? Have you completed? Now, clear. Okay. What is Ampere's law? Ampere's law, the statement of Ampere's law says, for an imaginary loop, integration B dot dl, this is line integration B dot dl, is equals to mu naught times current enclosed by the loop. Okay, I will explain each and everything. First, let me know how many of you are aware of this Ampere's law and how to use this Ampere's law. This is the statement. This is one thing. B dot dl is equals to mu naught times current enclosed by the loop. What are the procedures or what is the procedure to use this Ampere's law? Let me explain you. Let's suppose there is a infinite wire. I am giving you a hint. This is an infinite wire, infinity, and again to the infinity. Now, what you want to do, you want to calculate the magnetic field due to this wire. So for that, there are few basic steps. First step says select a symmetric loop. Select a symmetric loop. What is the meaning of symmetric loop? Symmetric loop means the loop which has same or nearly the same shape of the magnetic field. Nearly the same shape of the magnetic field. For a long wire, you know from the Oster's experiment, the magnetic field lines are like that. This is the direction of magnetic field for a long wire. Now you need to choose the loop in the same shape. So my loop is also in the same shape like that. Okay. Another thing is second step, give a sense of rotation to the loop. Give a sense of rotation to the loop. This is your choice. You can give any sense of rotation. I have given a sense of rotation like that. This is the sense of rotation on the loop. This loop doesn't have any current. This is the sense of rotation. Okay. Now, third step, apply Ampere's law. Now, there are two things that you should remember. One is the statement says current enclosed by the loop. For example, if my loop has two wires like this, one wire which has a current in the upward direction, let's suppose I1, and another wire has a current I2 in the downward direction. Then what will be the value of I enclosed? What will be the value of I enclosed in this situation, in this diagram? Can anyone answer? What will be the value of current enclosed inside the loop? I enclosed will be one current in the upward direction, one in the downward direction. Then the net current will be the difference of these two. Will be the difference of these two. And if you see the difference of these two, you will see it will be I1 minus I2. It will be I1 minus I2. Clear? So I enclosed, you can write it like that. One more thing that it will take again a lot of time. So let's keep it simple. I am not going to discuss that thing because it will take another lot of time. You will need more understanding of that. It might be written as I2 minus I1 as well. It depends on the sense of rotation. It depends on the sense of rotation. If you want to ask, any one of these can be written. But in this particular diagram, this one is correct, this one is wrong. But in some other diagrams, it may be correct. Some other diagrams. So it depends on the sense of rotation. If you want, I will explain. Otherwise, it's not that important to understand. But sometimes question may be asked from this. So if you ask, I will teach you later because today's time is over and chemistry, I think sir will be waiting. Okay, so let's revise. You should revise all the things we have covered. Biot-Savart law, its application, loop, straight wire, Ampere's law, a part of Ampere's law. Now, next will be uh, the magnetic force, velocity selector, cyclotron type of things. So we will discuss. Till then, in the second part, till then, enjoy, study hard, make use of all the things. Bye. If you want anything, if you want to ask something, if there is 2 minutes time or 1 minute time, you can ask. Otherwise, I am leaving the session. Thank you. Thank you, everyone. Thank you, Bhagishri, Gauri. Okay, I'm ending the session. Bye, everyone. Where is that? Bilkul, Deepak. You can get the PDF. Very good. I think, Deepak, you have written it in Hindi. You understand Hindi. That's very good. मिल सकते हैं दीपक ये सब आपको